Hello everyone. Today we are going to discuss Hamiltonian dynamics. Okay, so let's get started. Hamiltonian dynamics. Okay, and this is our class number 2. Right? Okay. Okay, let me add a few pages. Okay. So before going into Hamiltonian dynamics, let us revisit some of the things that we have already learned. So first thing that we learned that the Lagrangian of a system denoted by L is a function of q dot, this is the velocities and time. Okay, and the Euler-Lagrange equation is given by del L by del Q I is equal to d dt of del L of del L by del Qi dot. Okay, and we have also defined an integral called exon integral denoted by A is equal to t1 to t2 L d t. Okay, and we said that a system moves from point A to B such that delta A is extremum. Okay, and we have this condition satisfied if we can show that the system obeys this equation that we have already solved. Okay, and we have also solved a few examples using this equation. Now the question is, why do we need to move from Lagrangian dynamics to Hamiltonian dynamics? Okay, the first thing to notice is that this equation is actually second order in nature. This is the second order differential equation. How is that? Because this variable q dot, it already involves differentiation with respect to time. Okay, that is the q dot. So we can write q dot is d dt of q, right? So eventually this turns out to be a second order differential equation, and this would be better if we could move from second order differential equation to first order differential equation, and that thing is achieved through Hamiltonian approach. Okay. Okay, so that's why Hamiltonian approach is kind of a better approach compared to Lagrangian approach. Okay, so before going into Hamiltonian dynamics, let us discuss something about Legendre transformation. Okay, what is Legendre transformation? Okay, my T and F's are almost same. Transformation. Okay. Okay. So for that, if we have a function, let's say we have a function, so arbitrary function f of x. Okay, if we have a function f of x, then we can denote this function f of x, or we can get this function exactly if we specify this value of this function. Okay, let me make this a straight line. Okay, at each of these values of x. Okay, okay, if we specify f of x at, if we specify f of x for each x. Okay, and we can also get the same thing. We can get the same function. We can get the same function f of x. Okay, this is my function f of x. If I specify the slope of this function. Okay, if I specify the slope of this function f is x, that is how also we can define this function, and I can get the exact function if we specify the slope of this function and value of the function at some point, let's say at 0. Okay, if we specify f of 0 and the slope. Why do we need to specify f of 0 or some f of some x? Because otherwise, if I only specify the slope, then you can always shift this function upward or downward. Okay, but if I specify that at x equal to 0, the value of this function is this, then I can get the exactly the same function which was initially defined. Okay, and the second procedure is useful if we have more than one variable in the system. Okay, so for that, let us define a function f, a function of x and y. Okay, we have df is equal to del f by del x dx plus del f del y dy. Okay, and this is nothing but some quantity dx plus some quantity dy, and which I denote as x dx plus y dy. Okay. So let's say, for instance, for some experimental purpose or for some simplification of this problem, we want to have a function z which could be written as some quantity dx, the capital X, plus some quantity dy, small y. Okay, and how do we get this? We can get this if we define z as f minus x into x. Okay, and one can verify that dz would be df minus x dx capital X minus capital X dx small x. Okay, so if we put the value of df, that is x dx plus y dy, then this would turn out to be minus x dx plus y dy. Okay, so how do we go from f to z? How did we go? We go using this z is equal to f minus xs. Okay, and let me simplify this. C is nothing but f minus the variable that you want, is a wanted variable, multiplied by the variable that you don't want. Okay, wanted variable and unwanted variable. Okay, and this is a nice thing to remember. and this will be really helpful in so many cases. And thing is, we have already used this formula in various cases, like while we studied thermodynamics. Okay, in thermodynamics, we have used this formula to deduce the free energy expressions. Okay, let me show you. Okay, we know that the internal energy U is the internal energy. Internal energy. Okay. Internal energy. U is a function of. Okay, let me write this. U is a function of S, T, and N, right? And we know du is equal to EdS minus PdV plus mu dN. Okay, this is the change in the number of particles in the system. This is the change in volume. This is the change in entropy. Okay, but the thing is, it is very hard to control this entropy in a system. But what we can do, we can control the temperature. That's why we want to have a function which should depend on T. We should depend on T and V and N. Okay? We want to have a function which should depend on T, V, and N. Okay? For which we have defined a quantity called Helmholtz free energy. Free energy by F. This is a function of T, V, and N. And we know that F is given by U minus ES. Okay. So where S is the unwanted variable that you don't want. The unwanted variable, and T is the one that you wanted, right? Okay, so one can show that dF would be nothing but du minus EdS minus SdT, right? And du is EdS minus PdV, EdS minus PdV plus mu dN minus EdS minus SdT. Okay, and this one cancels out, and we are left with, what do we left with? We left with minus PdV minus SdT plus mu dN, right? So F is a function of T, V, and N. Okay. Similarly, we can go to Gibbs free energy, where it would be a function of T, P, and N. Okay. Right. So how do we do this? We do this like Z is equal to F plus PV. This is plus. Okay, this is plus because we already have a negative sign here, minus PdV, and if we put plus PdV, then this will get cancelled out, and we will left with VPP, and that would lead to Z is a function of P, P, and N. Okay, and these are the things that where we have used legendary transformation. We have used legendary transformation, right? Okay, and we are going to use the same thing while we deduce the Hamiltonian dynamics. Okay. Okay. We are going to define the set of equations which should lead to Hamiltonian dynamics. Okay. Okay. So we know that this is the Euler-Lagrange equation. Del L by del Qi equal to del L. Oh, sorry. ddt of del L by del Qi. Okay. And now we are going to define a quantity called generalized momentum. It was going to define a quantity called generalized momentum EI. This is given by del L by del Qi dot. Okay, and that's how we get rid of this velocities. We get rid of velocities, which you don't want. Okay. Okay. So let me say a few things about this generalized momentum. So this generalized momentum is sometimes also known as canonical momentum. Canonical momentum, or sometimes also known as conjugate momentum. Okay, and if we have a cyclic coordinate Qi, if we have a cyclic coordinate Qi, okay, then this will lead to a constant of motion. To the corresponding generalized momentum. How can we see that? We can see that if Qi is a cyclic coordinate or an ignorable coordinate, then del L by del Qi is equal to 0. It means this Lagrangian L does not depend on some particular Qi. Okay, that leads to del L by del Qi is equal to 0. Okay, and if we put this in Euler-Lagrange equation, then Euler-Lagrange equation will lead to ddt of del L by del Qi dot is equal to 0. Okay, this ddt of EI is equal to 0. Okay, we should say EI is a constant. Okay, so this is true for every system where if we have a cyclic coordinate Qi, then the corresponding generalized momentum would be a constant of motion. Okay, so now let us use the Legendre transformation. Okay, and where we define a quantity called is, we should be dependent upon this position coordinates Qi and Ei and T. Okay, and we want it okay, Qi dot, that is we don't want, and Qi P minus L. Okay, so the thing is, it should have been defined like L minus sum over I Qi dot Ei, but historically it was defined like this, and the reason for defining like this is because H turns out to be the total energy of the system, mainly in mechanical systems, and we want it to be positive. Okay, and here only sign has been changed and nothing else. remember this. Okay, and I should write it like is qi pi t equal to sum over I qi dot pi minus L qi dot mt, right? Okay, so if we have understand till this, then we are actually in a good set, and we can move to a Hamiltonian dynamics. Okay. Okay, so okay, I can write this in a short form like is equal to q dot p minus L. Okay, and then I do the is equal to what would be this? This would be q dot dp plus p dq dot minus dl, right? And we can write q dot dp plus p dq dot minus. Now we have already seen that dl is equal to del L by del Q dq plus del L by del Q dot dq dot plus del L by del T. Okay, we are going to put it here. Okay, then this would be del L by del Q dq minus del L by del Q dot dq dot minus del L by del T. Okay, so q dot dp plus p dq dot minus del L by del Q dq, and del L by del Q dot is minus p dq dot minus del L del T, right? Okay, and these two cancels out, and we have this nice equation q dot dp minus del L by del Q dq minus del L d, and sorry, there should be dt, right? dt, sorry, right? Okay. Again, okay, let me number this equation as equation number 1. Again, the is should be del is by del Q dq plus del is by del T dp plus del is by del T dt. Okay, this is equation number 1. And now we compare this component. Okay, we compare these components from equation 1 and 2. Okay, from equation 1 and 2, what we get? We get, okay, from equation 1 and 2, we get we get q dot is equal to del is by del p, okay, and del is by del q is equal to minus del L by del Q. Okay, and del is by del T is equal to minus del L by del T. Okay, again del L by del Q is equal to d dt of T, right? Since del L by del Q dot is equal to T, okay, where E dot is equal to del L by del Q. Okay, if we put it here, then this should be minus del is by del Q. Okay, so finally we have what do we have? We have Q dot is equal to del is by del T, and E dot is equal to minus del is by del Q, and del is del T is equal to minus del N del T. Okay, please remember these equations. Okay, and these are Hamiltonian equations. These are Hamiltonian equations. Okay. Okay. So you can see from here that these equations are first order in nature, right? And please mind this negative sign, and this negative sign is very important. In a few minutes, we are going to see why. Okay. Okay. So let us consider a Hamiltonian case which does not depend on time explicitly. So this is the function of Q and P. Okay. Then if I do d dt of S, then this should be del S by del Q dq dt plus del S by del P dp dt. Okay, and this should be del S del Q dot plus del S del P, and this is P dot. Okay, and we know from these Hamiltonian equations that we know that del S del Q is Q dot is equal to del S del P minus del S del P and del S del Q. Okay, and this is equal to 0. if the Hamiltonian does not depend on time explicitly, then it is a constant of motion. Okay, this is a if is does not depend on time explicitly, then is a constant of motion, and this is always true. Okay, so if there is a quantity which is a constant of motion, then what would be its general criteria? Okay, let's find out. Okay, let us define a quantity. Let's say f which depends on time. Okay, and suppose this is a constant of motion. Okay, and then for that, if f is a constant of motion, then df dt is equal to 0, right? Okay, let's find out what is df dt. df dt is equal to del f by del t, and this will be q dot plus del f del t p dot plus del f del t. Okay, and using Hamiltonian equations, del f del t okay, so let's find out what is df dt. Okay, and df dt will be equal to del f by del q dot plus del f by del p dot plus del f del t. Okay, using Hamiltonian equations, del f del q dot is del p minus del f del p del q plus del f del t. Okay, and this quantity we can write as f is del f del t, and this quantity is known as boson bracket. Okay, so if f is a constant of motion, then this relationship has to be satisfied. Okay, okay, so that's all for today, and in the next class we are going to talk about boson bracket and its properties. Okay, and we will also do a few examples. Okay, thank you.